Okay, so let's start. So last time we finished with last time was 2 weeks ago. So we finished with the gauge system. We arrived at the gauge system. So in an arbitrary metric, the gauge system has the form so the general topic is still continuing BRST. So so the ghost action is and we had the so B and C are the ghosts. So these are the ghosts, and B is a symmetric tensor. And we have an additional constraint that B is traceless. So gamma alpha beta B alpha beta should be 0. And well, gamma here is the reference metric. So this is kind of implied that gamma is some reference metric. And it is useful to keep this metric, for example, for the calculation of the energy momentum tensor of the system, right? So the energy momentum tensor, so the gauges, they contribute to the energy momentum of the system. So the variation with respect to the metric will give you the energy momentum tensor. But eventually we want to go to conformal gauge, meaning that we pick gamma equal to the unit matrix. So let's do that. So that's for an arbitrary metric, but actually we want to set to go to conformal gauge. So we want to set gamma or delta. So the important property of the system also is that it's while invariant, just like the matter system. It might not be immediately obvious, but in the way it's written, it's precisely while invariant. So so this thing is while invariant, and then the Christoffel symbols and so on do not spoil it. So this is while invariant. So kind of check this. This really depends on the fact that we've written C with an upper index and B with lower indices. So if you lower or raise the indices, then your fields might become charged under the Weyl symmetry, right? So, I mean, when you lower or raise the indices, you contract with the metric, and the metric contributes extra factors of contribute to the Weyl transformation. So here, I mean, while invariant, meaning that B and C are uncharged. Means they do not transform under the Weyl transformations. Okay, so then since this is a diffeomorphism and a Weyl invariant, we can go to conformal gauge. So that means we can set gamma equal to delta. Well, actually eta, right? So far we are in Minkowskian signature on the world sheet because I have a minus here. So let's set gamma equal to eta, and then define that the ghost action simplifies and has the form So actually, I'll write that Sx plus S ghost. So the full action has the form so this is the matter part. Has this simple form. So C has components C plus and C minus, right? And B is a symmetric tensor, so it has components B plus plus, B minus minus, and B plus minus, but B plus minus is 0 due to this condition. So when we set the metric equal to the diagonal matrix, we find that B plus minus is 0. So this is the trace of B. And only two components actually survive. So this is how the matter plus gauge system. So this is the full system looks like in conformal gauge.
Sorry, why are you doing this?
Well, we're studying the system in conformal gauge, right? So these are the ghosts that are present in conformal gauge. So in light cone gauge, there are no ghosts. So the ghosts are some auxiliary fields that arise in non-physical gauges. And well, ultimately, we wanted to show that this has a BRST. This is BRST invariant, right? So it has a BRST charge, nilpotent BRST charge, whose cohomology kind of gives you the same construction as the the long construction that we discussed before in conformal gauge, where we have some spurious space, we have physical space, and so on. So that's that construction is in one-to-one correspondence with calculation of cohomology of BRST charge. So in principle, that's the logic. I mean, in fact, I don't think we will really discuss the cohomology of the BRST charge, but we will just discuss some other interesting properties that are related to it. But in principle, that's why these ghosts appear. So they allow to bring this description of physical, unphysical, and so on states in your Hilbert space in a like cohomology-like problem. So that's the idea. And same stuff happens in electrodynamics, for example, in Lorentz gauge. So in Lorentz gauge, you also have some unphysical polarizations. So to get to the two physical polarizations, you have to compute the cohomology of the BRST charge. And in many other systems with where you fix the gauge. So, I mean, last lecture, or don't remember exactly when we started that, but we were discussing BRST transformations in usual finite dimensional integrals, where we're integrating over the quotient space. So there's some group acting on a manifold. Yes, we're integrating over the quotient space. The quotient space is viewed as some submanifold in the original space, right? That intersects every orbit of the group action, and there is some measure induced on that surface, and that measure can be nicely encoded by. I mean, it involves some determinant which can be nicely encoded in some. By some anti-commuting fields that we call the ghosts. So this is similar thing in an infinite dimensional setup, where your manifold is the space of fields on some other manifold, and the group acting is the gauge group. So I mean, that's the general idea. I realize that it's a big leap from finite dimensional integral to this kind of infinite dimensional system, but I hope kind of vaguely it's clear. But apart from this general logic, I mean, this BC system is an interesting system of conformal field theory that's quite ubiquitous in its own right. So this is still a conformal field theory. So the X system was a conformal field theory to start with. You remember we derived its energy momentum tensor, TZZ, T plus plus, T minus minus. So this is also a system of conformal field theory. And to see that, we should look at the transformation properties of the B and C fields. So, so the point is that these terms are conformally invariant. So this is, I hope, obviously conformally invariant, right? You reparameterize. So you reparameterize sigma plus is minus tilde, and the derivatives, the factors of the Jacobian that come from the derivatives cancel against the measure, right? So that's the general property of any sigma model in 2 dimensions, classically, right? And these guys are a bit somewhat more involved, because you see, if we just make this change of variables, you get one factor of d plus over d plus tilde from the derivative, which cancels against the factor from here. But then there is another factor corresponding to the sigma minus reparameterization coming from here, right? And it has to cancel against something as well. So to cancel against something, we will assign certain transformation properties to the B and C fields. So for example, here the x's were transformed trivially under conformal transformations. Here it cannot be the case, because otherwise you don't get invariance. So so the transformation properties will be as follows. So we will say that B minus minus so these are the transformation properties where J is 2. So J so the reason why J is 2 is that, well, you see B is a 2 tensor and C is a vector, right? So these are precisely, if J is 2, these are precisely the transformation properties of a 2 tensor and a vector. So that means that, let's say, B minus minus dx minus squared. So this transforms as a tensor of rank 2. And let's say C minus is a vector. So it's, oh, sorry, this should be sigma minus. So in general, these were just generic tensors on our manifold, but once we've picked conformal gauge, the remaining diffeomorphisms are the conformal transformations. And so this is how it transforms under those remaining conformal transformations.
Here is it Jacobian or some Berezinian?
No, it's just a Jacobian. So
B are both.
yeah, I mean, okay, this is the transformation. I mean, no matter how you wish to call it. So this is the explicit form of the transformation. So the reason I've put J here is that actually the system is conformally invariant for arbitrary value of J, right? So the important point here is that the sum of the powers of these guys is equal to 1, right? The reason is that we want to get one factor of d sigma minus over d sigma minus tilde, for example, in this term, to cancel against the factor coming from the measure, right? d sigma plus over d sigma plus tilde cancels against the derivative. And the sigma minus over the sigma minus tilde has to be cancelled by the transformation properties of the fields, right? And how we redistribute these weights between C and B is actually kind of undetermined from the form of the system. But it is determined from the physical input that these actually come from tensors on our manifold. And the fact that these are tensors of, for example, rank 2 has to do with the fact that, remember, B was a kind of partner of capital B, which was the Lagrange multiplier fixing our conformal gauge, right? So remember, there was also some capital B, which was B alpha beta, which entered the Lagrangian in this form, and BRST transformations were relating small b with capital B. So that's why B is a tensor of rank 2 and C is a vector because, as we discussed, C plays the role of a parameter of our gauge transformation. So for diffeomorphisms, the parameter of a transformation is a vector field. So C becomes a vector field, right? That was the logic. So, and then this ultimately leads us to the fact that J is 2 in this CFT. So once if we just simply wrote down this action, J would be in principle arbitrary, but this is fixed from the fact that it's actually a gauge fixing of a action where B and C are tensors of corresponding ranks.
So it's like for this particular value of J, our theory will be like conformally invariant.
No, it's conformally invariant for arbitrary value of J. So J is a physical input. It's not dictated by the form of the theory.
Can you repeat how did we find the value of J?
It comes from the fact that B and C were tensors of the corresponding ranks. So B is a tensor of rank 2, C is a vector. So kind of if we think of tensors as tensors with lower indices, this is tensor of rank 2, and this one is tensor of rank 1 with an upper index. So kind of -1 in this notation. You see, that's why you have J is 2, here it's -1. So that's how it comes about. But in principle, this is a conformal field theory for arbitrary J. So let's derive its energy momentum tensor. So once we know the transformation properties of the fields, we can derive the energy momentum tensor of this BC system, right? So this is called the BC system, yeah.
Am I right, like J is corresponds to something like weight?
Yeah, exactly, yeah. Conformal weight, yes. That's right. And accordingly, we have similar weights for B++ and C+, right? But under the left-moving conformal transformation. So these are only charged under transformations of sigma minus. These are only charged under transformations of sigma plus for the same reason. That's right, J is the weight. So B has weight J and C has weight 1 minus J. So let's derive the energy momentum tensor. To this end, what should we do? Well, we should make this we should make some by Noether's method, right, we should promote these transformations to local transformations, meaning, well, they're already local, kind of, but we should let them depend on the second variable as well, right? So, so let us say that sigma minus is sigma tilde minus plus f of depending on both sigma minus and sigma plus, and sigma plus is we don't change sigma plus, and we want to derive the energy momentum tensor of this part of the system. So similarly, you can derive energy momentum tensor for the second part. So first of all, yeah, so first of all, we find that the plus, so we'll compute the variation of all of these fields. So d plus c minus is d plus tilde c minus minus d plus tilde f times d minus tilde c minus. So this is just formula for the change of variables. But then we know that C minus is from that formula over there, C minus tilde 1 plus J minus 1. So so substituting this here, we find that d plus c minus is d plus tilde c minus tilde times 1 plus okay, so this is just a formula that you get by substituting all the transformations, and then we also have the formula for B minus. So this is and this is all to linear order in F. Yes, so this is plus. So we don't care about higher orders in F. And so now you substitute this in the action. So the action S, depending on B minus minus and C minus, is d2 sigma tilde then minus tilde f minus, and then you d plus c minus, and here you substitute this huge beast. but everything nicely simplifies. So you get this is S. After some integration by parts. So you get this answer. So the variation of the action is this thing here. So for F independent of sigma plus, this is a symmetry because this is just a conformal transformation. But for F depending on sigma plus, now we have a variation which has to vanish by the equations of motion. Therefore, this guy here is the energy momentum tensor. So T minus minus is proportional to this thing here. And I'll remove the tildes now, just not to. And the property is that it's conserved in a chiral sense. So this is the main upshot of this calculation. So basically we just used Noether's method. We do a transformation depending on space-time coordinates. We find a piece on the variation proportional to the first derivative. So this gives rise to a conserved current. So this is T minus minus, and T plus plus will analogously involve B plus plus and C plus.
So what is this S here, the first term?
Which first term? This?
Yes.
Well, this is the variation. So I mean that.
We had XX plus S cos, right? We had SX plus S cos.
Yeah, right. So now we only concentrate on this part with B minus minus and C minus ghosts. So S is the, as I've indicated here, is just the part that depends on B minus minus and C minus. Right? I mean, all three pieces are separately conformally invariant. So for each piece, you can derive its energy momentum tensor. And the full energy momentum tensor is the sum of three terms. One coming from the X part, which was D plus, or let's say the T minus minus part was D minus X squared, right? Then you have this piece, and the plus plus part will have D plus X squared plus the term with B plus plus and C plus. So that's the okay. So now we will derive these guys also in Fourier modes, decompose these guys in Fourier modes, derive the corresponding expressions. So you remember that, yes, we had that D plus X squared expression, D minus X squared expression for the energy momentum tensor. Then we expanded the X fields in Fourier modes, and we got some combinations quadratic in the oscillators, right, of the field that we called Ln, the modes of the energy momentum tensor. So here, similar thing can be done. So Fourier modes, we will consider here the closed string case where the boundary conditions are simpler, meaning that we will just say that C plus and C plus, B plus plus, we should write C plus is periodic. So in the case of, so this is closed. Closed string case. So in the case of the open string, you have to deal with boundary conditions, and this is a bit involved, so we will skip that part. But the point is that, so for the upshot for the open string is that you have to have that C plus is C minus and B plus plus is B minus minus at the ends of the string. So you would have to the boundary conditions are dictated by the symmetry. So the BRST symmetry will dictate that some certain boundary conditions are satisfied. But we will drop this part and just consider the simpler case of periodic boundary conditions, where we can just expand C's and B's in Fourier modes directly. So C plus is, for example, C plus is Cn I to the In sigma plus, and B plus plus is Bn and we can as well canonically quantize this action, right? It's already in first order, this action, it's already in first order form, so it's clear that B and C are canonically conjugate variables, right? So canonical quantization says that B and C just obey these commutation relations. And now what we want to do, we want to substitute this expansion in the energy momentum tensor. Well, sorry, these were the minus components here. Well, analogously, you have everything for the minus components. And you want to decompose this T minus minus and T plus plus in Fourier modes as well, right? And the coefficients will be these lns of the ghosts. So we'll define ln C, C meaning it's a ghost. So this is a is the integral of 0 to 2 pi of T plus plus of T plus plus C. So C is the ghost energy momentum tensor, and this gives an expression like this. So I've put normal ordering here straight away, kind of assuming that this is all quantized. Again, you only need it for the zeroth component. So this is a definition, if you like. I mean, the fact that we normal order here. And ultimately, we'll again set j equal to 2, but this is kind of an, as I said, an interesting conformal field theory in its own right, so that makes sense for arbitrary j. So you see the energy momentum tensor roughly has two types of terms, right, where the derivative acts on C and the derivative acts on B. So the relative coefficient is what encodes J, effectively. So when we discuss the modes of the energy momentum tensor of the X fields, we computed its commutators, right? And we found that there's this anomaly, central charge anomaly in the Virasoro algebra. So the next step would be to compute what is the anomaly coming from these guys. So that's what we're going to do next. So the first thing is that it's easy to check that for m plus n not equal to 0, then we have the standard commutation relations. So the only ambiguous terms, or I mean the terms that are behave non-trivially under quantization, are the ones with m equal to minus n, just as before. And just as before, we should, to find that contribution to the central charge, what we should do is we should find the terms that have two creation operators and two annihilation operators, right? Creation and annihilation operators are defined via this exchange relation. By the way, this is a anti-commutator, not a Poisson bracket. Yes. So B's and C's with positive values of the index are annihilation operators. The ones with negative values of the index are creation operators. So the relevant terms are, so for n smaller than 0, so kind of safe terms plus sum of k plus n smaller than 0, and then so this is k minus and for n greater than 0, so we'll be computing two terms, one with negative n, one with positive n, right? So so here both terms are creation operators because k plus n is negative, and this one is also negative or non-positive, let's say. So so here both terms are annihilation operators. So these terms, they involve one creation, one annihilation operator. So there is no problem with them. So and now we compute these two guys. Find that is a normal ordered part. Minus So I mean, I will not do the calculation, but you need to commute these two terms and reorder them after you commute. And then you get some remaining sum, which is computed and gives this. Then we set j equal to 2, and we compute the total central charge. So the full ln is ln coming from the x part plus ln coming from the c part. So when you calculate the commutators, there will be part in the central charge coming from the x fields and part coming from the BC ghosts. So the total central charge turns out to be d minus 26 over 12. And so miraculously, this is exactly 0 for d equal to 26. So this is kind of the main reason for calculating this central extension of the ghosts, to find that the total central charge will be 0 for d equal to 26. But of course, this needs to be explained, right? So the question why? The question is why? And that's what we will do in the second part of the lecture, I think. The main answer is that this is related to the vanishing of the while anomaly. So throughout this course, we've been discussing that while symmetry is quite important for our system to be gauge invariant, right? We use while symmetry to go to conformal gauge, for example. And so there are symmetries that are symmetries classically, but not they lose this property upon quantization, right? So these are called anomalies. So if you want the quantum theory to be gauge independent, so for example, to have a match between light cone gauge and conformal gauge, that's as a simplest manifestation of gauge independence, you should make sure that the anomaly also vanishes. And we will discuss after the break that actually the anomaly is proportional to the central charge. So this is a general property of such theories. So you could take an arbitrary conformal field theory with some central charge and couple it to gravity, means couple it to the metric. And you can ask if this theory is while invariant. So the obstruction to while invariance will be the non-zero central charge. Of course, in principle, in an arbitrary CFT, there is no reason to require while invariance, right? So CFT is defined in flat space, and this is just our wish to couple it to some metric, and C is just basically gravitational susceptibility of your system, right? It's just how it reacts to gravity, how it reacts to a non-trivial background metric. So it doesn't have to be zero, just like, say, electrical or magnetic susceptibility doesn't have to be zero, right, of some material, let's say. But in this particular system, this string theoretic system, where we actually insist on while invariance being key property of your theory as part of the gauge symmetry that we actually use, we do require the central charge to be zero, and that's what the ghosts also incidentally do for you. So once you include this ghost part of the CFT, it cancels the central charge of the matter part. And altogether, matter plus Go system is while invariant. So, before we come to the discussion of the while anomaly, let's just observe one other curious fact about this central charge being 0 that has to do with the BRST charge. So as we already discussed in the first half, in principle, this BRST charge is rather convenient in that its cohomology describes the physical states. So let's take a brief look at this BRST charge. So first of all, well, there are the BRST transformations. So these are some global transformations. So as we discussed before, so BRST are global transformations. So they lead by Noether's theorem, they lead to a conserved current. Conserved current. So if you actually derive it, it has the following form. So J plus is this is actually the same as C plus times T plus plus X plus 1/2 T plus plus C. And it satisfies the conservation equation D minus G plus equals 0. Analogously, there is a G minus satisfying D plus G minus equals 0. It is a bit lengthy derivation, so we derive the BRST transformation. So you take that free, so you take the free action, although it's kind of simple free action, but the transformations are somewhat complicated. So in the end, you get this cubic expression for the current, clearly then you can also derive the charge, the BRST charge. So the BRST charge has the form that is C minus N ln tilde X maybe let's just ln C. It's ln C, so C minus N ln X plus 1/2
I'm sorry, is the expression in the brackets?
Yes.
Is it not conserved? The Tx plus 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 1/2 Tc plus plus, is that not conserved? Like T minus of that thing is not 0?
No, the minus of that is 0. Why?
But then if we act on that thing with T minus, it will just leave, so it will be just C minus, like T minus C plus times that thing equals 0.
Yeah. But C plus is also, D minus C plus is 0 by the equations of motion.
Sure, but I think that we know both of these. We've proven this for like the energy momentum tensor just now, and we know that from the equations of motion. So it's like a trivial fact, or, well, not trivial, it's just, I don't think we could have guessed that this is conserved.
Well, I mean, every charge, Noether current is conserved by the equations of motion. So it can be derived by somehow superimposing equations of motion with some coefficients, basically. So yeah, here it's a combination of, yeah, you can view it as a combination of those two facts. That so, but the key property will be that this charge will be nilpotent, right? Which is in general not true. For example, if you pick here arbitrary linear combination, that will not be true. So that's the key property. Also, another nice property of this particular combination is that the anti-commutator of Q with Bn is ln. So this is ln x plus ln ghost ln c. Right. So the point here is that when you commute with b with c gives 1, so it gives ln x, and here you have c twice, so you get a factor of 2, which cancels this factor of 2 here, and what remains is precisely the energy momentum tensor of the ghosts. So this is the main relation that we want, and so the energy momentum tensor is the variation of the B field, basically. That's what it says.
This charge is conserved, right? Q.
Yes, this charge is conserved, yes, which follows from the conservation of the current that it's derived from. So this is the current corresponding to the this is the charge corresponding to this current. So we will discuss it now. Yeah. So that's the statement. Yes, that q squared is 0. Yes, but let's derive that. So first of all, let's compute the. So using that last relation, let's compute the commutator of ln with lm. So this is the commutator of ln. So this is the full energy momentum tensor. So this is ln Q with Bm. So now we can use Jacobi identity to change the order of commutators. So here this is. So we find that this is the commutator of ln with Q. ln with Bm. So the commutator of ln with Bm is n minus m times Bn plus m. So this follows from the explicit form of the of L. So here we only care about the ghost part, right? Because the matter part trivially commutes with B, and L is proportional is linear in B and linear in C. So you commute B with C, one b is left, and the coefficient comes from the explicit expression of L. And now this guy, again using this expression here, is n minus m times L n plus m. Right? So this is the first term in the right-hand side of the commutator of the L's. So one can guess then this term will be responsible for the anomaly. Right? And indeed, we can compute, so commutator of Ln with Q. What is it? So again, we use that expression there. So this is the commutator of Q with Bn with Q. And so this is the commutator of Bn with Q squared. So this you just open the brackets, just write explicit expressions for the commutators if you find this. So you see if Q squared is 0, then this extra piece vanishes. So actually, so Q squared is 0 is equivalent to center of charge being 0, the full center of charge. Total. So here it's so it's obvious that if Q squared is 0, then this term is 0, right? But you see, this term is therefore equal to the, so it's a double commutator of Q squared with B, right? And you can. If you think a little bit about it, you will realize that Q is always Q squared is quadratic in C. So this is obvious for this first term, but then when you compute the commutator, you will compute this guy with this guy, and ultimately it will be quadratic in C. So the general form of Q squared is that this is Ck C minus K times Rk, where Rk are some coefficients. And in that case, so if that's the form of Q squared, then you can compute twice with B, right? And you find that this double commutator is proportional to Rn times delta n plus m. Right, so on general grounds, Q squared will be a quadratic combination in the C's. And what stands here is a double commutator with B's. So each commutator removes one C, and you will get precisely this term. So this is the central extension in the algebra, right? So what we've derived from here is that Ln with Lm is n minus m Ln plus m plus Rn delta n plus m, where Rn are the coefficients in Q squared. So Q squared, this therefore proves that this statement, right? Because we know the central extension can only be of the form C times cubic combination in N. The vanishing of the total central charge is also necessary and sufficient for the BRST charge to be nilpotent.
For this information, can we relate get something Q with isospin, spin or hypercharge?
No. I mean, it's unrelated. I mean, yes, no, it's unrelated to the standard model in any way. I mean, yeah, that's a bit different course. I mean, yes. So. That's not. This was just an argument that the vanishing of the central charge is also important for Q being nilpotent, and that in turn is important for us being able to define its cohomology, which we will not really do, but we will just make the statement that the cohomology of Q is isomorphic to the space of physical states with positive norm. So, which in turn is isomorphic with the light cone gauge Hilbert space. And now we will pass to the topic to the discussion of the Weil anomaly and why actually why the Weil anomaly is related to the vanishing of the or non-vanishing of the central charge, or the vanishing of the central charge is related to the absence of Weil anomaly. So as I mentioned, these statements about anomalies, they apply to arbitrary conformal field theories coupled to something, right? Say coupled to the metric. But we'll take some concrete theory just to be more clear. So we'll consider free fermions. Let's consider free fermions in 2D. Okay, so this will be a bit far from what we're doing now, but it will be clear that it's actually very, very much related. So this theory of free fermions has this form. Well, it could be either in 2D or in 4D actually, but ultimately we want to be in 2D. So these are massless free fermions, okay, because we want to have a CFT kind of. So this has a U1 symmetry, right? So U1 what is called vectorial symmetry, which acts as follows: that rotates the fermion by phase, right? Here, gauge anomalies, I'm talking about chiral anomaly, what is called chiral anomaly. So that's why this is an anomaly in some symmetry called chiral symmetry. So that's what I'm defining first. So there's this vectorial symmetry, but then for massless fermions, you also have the axial symmetry, right? Axial symmetry, which acts by rotating psi by I alpha gamma 5 psi. And gamma 5 is just, so in 4D, this is gamma 0, gamma 1, gamma 2, gamma 3. So this is in 4D. So in 2D, we just define this as gamma 0, gamma 1. You could call it gamma 3 therefore, but just like to keep this. So this free theory has these two symmetries. And then one has a corresponding conserved current. So conserved currents. So J mu is psi bar gamma mu psi, and J mu chiral is psi bar gamma mu gamma 5 psi. right? So you can derive that as an exercise by Noether's theorem. So the question about chiral anomalies is the question whether these symmetries remain once we introduce a gauge field. So these currents are conserved in free theory. So in free theory they are conserved, so d mu j mu. But now we introduce a gauge field. So gauged is psi bar and the question is that still true that they're conserved? Those currents are conserved. So in other words, we want to check whether the correlation functions such as d mu x, j mu of x, j mu 1, j nu k yk, so is 0, and analogously okay, so we study correlation functions of the divergence of a current in the presence of some other currents. So the first current can be either vectorial or chiral, and the other currents are all vectorial. So in other words, this is the same as asking whether this guy is 0 in the presence of the gauge field, right? Right. So expanding our this correlation function is given by some path integral. You can expand it in powers of a. This will give you insertions of the j current. So these correlation functions are just expansions of your partition function in a. So the problem, what can be the problem? So the problem comes from divergent diagrams, those diagrams that are divergent. So what are these diagrams? So this is the diagram that looks, basically there's a single diagram. So here we have, this expansion of your A in your A. So, and this is your current here. So maybe let's draw like this. So this is either J or J chiral, right? Because why? Because the propagator behaves as 1 over the momentum. So this is 1 over the momentum. This is 1 over the momentum, and you integrate over 2 components of momentum in 2 dimensions, right? So this is logarithmically divergent, right? All other diagrams, so if you have diagrams like this, or more external legs, they will have more powers of momentum in the denominator, so they will be convergent. So there's no issue with those diagrams. So this is the only dangerous diagram. By the way, in 4D, so the diagrams that contribute, they depend on the dimension. So for example, in 4D, this is just as a side remark, so in 4D, there is a famous triangle diagram. So it contributes to the chiral anomaly because it's divergent in 4D. So the question is, so are these guys 0? And well, in principle, you have to do honest calculation, And what does it mean in anonymous calculation? That means you have to regulate those divergences. So how does one usually regulate divergences? Well, for example, you can add additional massive fermions coupled to the same gauge field. Either massive fermions or massive bosons. So the point is that you want to have additional diagrams of this form coming from with the opposite sign that will cancel the divergence. And then you send the mass to infinity eventually, the mass of those fields to infinity. Okay? And what you will see is that, so at each step, the diagrams will be convergent. So only something can happen when you send the mass to infinity. So the thing that happens when you introduce those massive fields is that you explicitly break chiral symmetry. Because chiral symmetry, mass terms are not compatible with chiral symmetry. So as a result, this correlator will be the problematic one. So the explicit calculation tells you that the two-point function of these guys is proportional to the transverse combination. So this guy is conserved. So if you multiply this with p mu, this is going to be 0. But if you take a correlator of the chiral current with the usual current, this will be of the form epsilon mu rho eta rho nu. And you see this current is not conserved. So if you contract this with p mu, this guy will disappear, but this guy will remain. Okay, so that's the signature of the chiral anomaly. So this correlation function remains 0, but this becomes non-zero. Okay, and so this is all these correlators can be encoded in the effective action, right? So we can compute, like I told you, these correlators are just expansions of your partition function powers of a. So you could just compute the partition function as a power of a, and then differentiate it several times, and get those correlators. So this partition function as a function of a is called the effective action. So this is defined effective action as the path integral where you integrate over psi's e to the psi bar a. Okay, so we compute the partition function. So this action is just the integral of this gauged Lagrangian. And this was computed by Schwinger, who found that the effective action is actually rather simple. It has the form f plus minus, but it is non-local, so it involves the 1 over the Laplacian or the Lambertian, depending which signature you work in. So it's kind of an exercise. You can, so homework, so problem, derive the correlators from effective action. So you differentiate it with respect to the gauge field, and you can derive these correlators. So why are we talking about that? Because, well, the point is that so what this effective action describes is the susceptibility of your free fermion system with respect to the gauge field. So you turn on the gauge field and you measure the response. Okay. So in the same way, what we want to compute is the susceptibility of our free system of, say, free bosons, X fields, BC fields, with respect to the gravitational field. Right? So the idea is that we can then replace A with our metric, A alpha with gamma alpha beta, and compute the effective action of the metric. So compute and then we will see whether this effective action is while invariant or not. Okay. So to make this even more clear, let's do the following thing. So let's write out this gauged fermion action explicitly in while components. So this is a Dirac fermion. It has two while components, right? So I mean, this is Dirac fermion. And for simplicity, let us, or for concreteness, let us switch to Euclidean space now. Okay, let's assume everything is in Euclidean space. So Euclidean signature. This is just somewhat easier because then it's easier to define inverses of operators like the Laplacian. I mean, dealing with boundary conditions is a bit easier. And also, the idea is that you can apply methods of conformal field theory to this description of this stuff. So, which is usually defined in Euclidean signature. So then the Lagrangian, this gauged Lagrangian, has the form that V okay, this is just V and U are just the while components of the Dirac fermion. You can rewrite that action in this form. And so, so AZ and AZ bar are two components of the gauge field conjugate to each other. So AZ bar is AZ bar in Euclidean signature. So you see, there's something special about this gauge field in two dimension that we originally introduced it as our U1 gauge field, right? It's a U1, the gauge field gauging the U1 symmetry that I talked about at the start, right? Psi goes to the exponent of I alpha psi. But curiously, it at the same time, it's a gauge field for the chiral symmetry. How do we see that? Well, what is the chiral symmetry here? So remember, I wrote out that we have the exponent of gamma 5 as the definition of our chiral transformation. But again, this is like leave it as homework to write it out what this is explicitly in this system. So the chiral symmetry here works as the combined, so vectorial and chiral, vectorial plus chiral symmetry. It works like this. So U is multiplied by some complex number, and V is multiplied by the inverse complex number. So lambda is a complex number. So it's not a phase, it's a non-zero complex number. Okay, so the vectorial symmetry is just U1 sitting inside here. And the second transformation is the radial multiplication by a real number. Okay. And now let's see. You see, you can transform the gauge field in such a way as to gauge that whole C star symmetry. So if you now say that AZ bar goes to AZ bar minus I dz bar of log lambda. So now you can say that lambda depends on z and z bar on your worldsheet coordinates. And this guy will be gauge invariant classically. Right? So it's some property of 2 dimensions. So we introduced one gauge field, but it's actually turned out to be kind of gauge field for this extended symmetry. But that's of course only true in the absence of anomalies in this second symmetry, in the chiral symmetry. So that's only true classically. But suppose this is true, there is no anomaly, so this is true quantum mechanically. Then what you have is you have one component of the gauge field, one complex component of the gauge field, and one complex complex gauge parameter. So you can actually gauge away your gauge field completely, right? So you can pick a gauge, when this is 0. So actually, in the absence of the anomaly, your theory is just independent of the gauge field. So kind of physically speaking, the anomaly in the system is good because it means the gauge field has some meaning. But what does it mean that if there is no anomaly? That means that the gauge field is topological. Okay, so gauge field is topological. So of course you can set it to 0 on a worldsheet of trivial topology. So say on flat space with decay conditions at infinity. If, for example, you have a cylinder, then you can still have holonomies around the cylinder. Or you have a Riemann surface, you can still have holonomies around the cycles of the Riemann surface. Okay, so you'll still have moduli space of connections. That's what I mean by saying it's topological. So in flat space, it's just 0. But the point is that I wish to draw a parallel with the dependence on the metric. Yeah. So in our string models, where the central charge vanishes and there is no Weil anomaly, the metric is topological. So you can effectively get rid of it. Or you, on a Riemann surface, you're reduced to the moduli space of metrics. So this is the same story, and just to finish, so I'll just kind of draw the I'll specify the main idea. So here you have vectorial gauge transformations. So U1 and you have chiral gauge transformations. So at the level of the metric theory, we will have diffeomorphisms and Weil transformations. So here we can quantize the theory in such a way as to preserve the vectorial U1 symmetry. And in the metric case, in the gravitational case, we can preserve diffeomorphism invariance. But we will, in general, one might not be able to preserve chiral gauge transformations if there is a chiral anomaly. And similarly here, there will be a Weil anomaly corresponding to the non-preservation of Weil symmetry. So, I mean, this is the gauge part, yes, this is A, and this is A alpha, and this is gamma alpha beta. So that's why I've talked about this gauge theory story, because here the effective action is simpler than in the metric case, but essentially it's the same idea. So in the metric case, in place of this diagram, you will have a diagram with two energy momentum tensors. So this is T and T. This is the kind of thing you have to compute the effective action. And this is what we will do next time and see how this effective action is proportional to the central charge. Okay, so that's it for today.